Circuits that contain multiple resistive, capacitive, and inductive components can be combined using the same rules for series and parallel methods used with resistors that you would have learned previously if all the values are first converted to impedances. For series elements, we use this typical series notation. The total notation ZT equals Z1 plus Z2 plus Z3. So this should just look exactly like the resistance formula. Right? So just keep adding them up. You can break that down. They do sum such that R1 plus R2 plus R3 plus J times X1 plus X2 plus X3, et cetera, et cetera, et cetera. This is also called the right-hand triangle method, noting that the impedance of the capacitors and the inductors are going to cancel each other out. So say we have a capacitor, we have an inductor, and we have a resistor, we need to add them. We just draw the inductor, or we draw the resistor, rather, on the positive real axis. We then draw the magnitude of the inductance. In this case, the inductance is larger, the inductive reactance is larger than the capacitive reactance, so the net result is just X sub L minus X sub C. So we're in the first quadrant. The resultant impedance is just, the additive of the X sub L's there. For parallel circuit elements, we use the 1 over Z sub T equals 1 over Z1 plus 1 over Z2 plus 1 over Z3, right? Plus da-da-da. Breaking it up into real and imaginary portions like that does not work for the parallel formulation. The best we can do is that's equal to 1 over R1 plus X1 plus 1 over R2 plus X2 plus 1 over R3 plus X3, right? We can't break the real and reactive components. Network reduction should be analyzed according to the same rules you've already learned for resistances, so that circuit branches are sequentially aggregated from the bottom up as series or parallel combinations up to the desired scale. And the main thing here is you need to treat capacitive reactances as a negative quantity. So let's do a kind of a simple calculation of complex impedances. We've got an electrical device. It contains resistance, an inductance, and a capacitance, all connected in series. Their values are R equals 1 ohm, L equals 0.01 henries, and C equals 0.001 farads. At an AC frequency of 60 cycles per second, what's the impedance of the device? And let's write that in polar form. So what we would do is we would draw the equivalent circuit diagram. First, we've got an AC voltage source. It is at 60 cycles, or 60 hertz, which we need to know to calculate inductive reactances. We don't need to know to calculate resistances. We've then got a resistor. We use the circuit symbol there. We've got an inductor, and we've got a capacitor. Right. So we know the values of these. We were 0.01 henries. 1 ohm, and 0.001 farads. Right, so those are the values. So what we need to do is use the frequency to convert over the reactances over to, the inductance and the capacitance over to reactances. So that would be done as X sub L. The inductive reactance is going to be equal to 2 pi F times L I'm using this because we were given frequency in terms of ordinary frequency. So 2 pi times 60 is 377 radians per second. You might think I'm really good at math. I actually just have that memorized. That is US AC Wolf angular frequency, 377 radians per second, which is equivalent to 2 pi times 60 hertz. Right, so I didn't actually do that mental math. I just have that memorized. You may also wish to memorize that for this course. So 377 radians per second. Now we need to multiply that by 0.01 henries. So we have a inductive reactance of 3.77 ohms. So we can do a similar math calculation for the capacitive reactance X sub C, that, if you recall, is 1 over 2 pi f C. So again, 2 pi f is going to be 377. In this case, we plug in 0.001 f. So it's 1 over 377 times 0.001 farads. The 377 is radians per second. I should have written that. So that gives us 2.65 ohms. So we've got, we can replace the 1 ohm device with its impedance, which is 1 ohm. This inductor is equivalent to 3.77 ohms, and this capacitor is equivalent to 2.65 ohms. So because these reactances are in series, we can use that right triangle method that we showed to combine them. So what we would say is that Z is just going to be equal to R plus J times X sub L minus X sub C. So here we have 100 ohms plus J. X sub L was 3.77 ohms. X sub C was 2.65. These all things in ohms. So this reduces down to 1.12 ohms. Right. So the whole quantity is Z is equal to 100 plus J 1.12 ohms. So that's the equivalent resistance.